Hi, this tutorial is on hydrogen 1 NMR or proton NMR. Hydrogen 1 NMR uses hydrogen nuclei, which are basically just protons, in exactly the same way as carbon 13 NMR uses carbon nuclei. Lots of the features of hydrogen 1 NMR are very similar to the features of carbon 13 NMR, but hydrogen 1 NMR is a bit more useful. It's more sensitive and it gives us a little bit more detail in the peaks. So here we've got a sketch of what a hydrogen 1 NMR spectrum might look like. And some of these features are very similar to what you see on carbon 13 NMR. So along the bottom we have the chemical shift value, which is again measured in parts per million, but this time instead of going up to around the 200 mark, in hydrogen 1 NMR it just goes up to 12, so it's a slightly smaller scale. And again we get peaks, which represent environments of the nuclei. So in carbon 13 NMR, each peak would represent an environment for carbon nuclei. In hydrogen 1 NMR, each peak represents hydrogen environment. So this chemical shift value can tell you about functional groups and about alkyl groups to give you an idea of what sort of environment your hydrogen atom is in. And the number of peaks along the spectrum also represent how many different hydrogen environments there are. So in that respect, it's quite similar to what you've seen before. Just to note, on this spectrum, we have 3 peaks. So this is one peak, this is another peak, this is another peak, and I suppose that's a small peak as well, so 4 peaks. So you can see straight away there's a lot more detail in this spectrum because this peak is very, very different to this peak, and these splitting patterns of the peaks do actually tell you quite a lot of information that's very useful for determining structures. Again, down here we've got this peak here. This is for TMS. So this is our standard to give us a value for 0. Again, we use it for all the same reasons as we do in carbon 13 NMR, so it is volatile, so you can easily remove it. It's inert, so it won't react with your sample. It's non-toxic, and so on. So TMS is tetramethylsilane. Now I'm going to look at some of the extra things that hydrogen 1 NMR can tell you that carbon 13 can't. First of all, we've got an integral pattern on a H-1 NMR spectrum. So integration is just the area under a curve. So the area under the curve, known as the integral. If you could look at that very closely, it's a little bit difficult to see on most spectra because you're kind of so zoomed out from the peak itself. But if you could look at the area under the curve, it would give you an idea of how many hydrogens are in that environment. Now, because it is difficult to see, a lot of the time you're given the values above the peaks. So this peak here represents one hydrogen environment because it's a peak on its own, and in that environment there is one hydrogen nucleus. So that gives you an idea. It can't be a methyl group, for example, because that would have 3 hydrogens in it. And the other peaks that we've got here, this one, can't quite see the integral underneath, can't calculate the area of the curve, but it tells you above there's 2 hydrogens in this particular environment, and there are 3 hydrogens in this particular environment. So that gives you a really good idea. So a lot of the time, when you see something worth 3 hydrogens, that could be a CH3 group. If it's worth 2 hydrogens, could be a CH2 group, could represent 2 hydrogens in the exact same environment, just in an alkyl chain. So the area under the curve or the integral is really, really useful. Sometimes you might see, rather than the numbers at the top, the 1, 2 and 3, you might see the symbol for integral. So this is called an integral trace, and it would look something like a tall S sort of shape like that. So that's an integral trace. And you might see one there, and you might see one there. So you can also use the integral trace as well to calculate this 1, 2 and 3 value. So what you would do is just use a ruler, measure from the top to the bottom of that integral trace, from the top to the bottom of that one, from the top to the bottom of that one. And if you calculate those as a ratio, you should get 1 to 2 to 3 to give you how many hydrogens you've got in each environment. So we've got the chemical shift value, which tells you about what sort of functional groups, what sort of environments you've got for each hydrogen nucleus. You have got the number of peaks, which show you how many environments you've actually got. Now with hydrogen NMR, we've also got the integral, which tells you how many hydrogens are sitting in that environment. And the final thing that this tells you is obviously the splitting patterns, so these weird peaks that are split into multiple smaller peaks. And these splitting patterns have a name. So this first one, this is called a singlet, obviously because it's on its own. Next one is called a doublet. this is a triplet, and this is a quartet. And you can also get something like that, which is known as a multiplet, one where you can't quite figure out exactly how many little peaks you've got, but just a big mess. So that's called a multiplet. And these tell you about neighbouring hydrogens. So if you've got a singlet, what that tells you is that on the next carbon across from where the hydrogen's sitting off, next carbon across doesn't have any hydrogens on whatsoever. So this could be something like this. So the peak representing these 3 hydrogens would have an integral of 3 to show that it's worth 3 hydrogens, but it would only be a singlet peak, because if you go one across, there are no hydrogen atoms on this carbon. A doublet shows that something has 1 neighbouring hydrogen atom. So these 3 hydrogens here, again, would have a tall peak with an integral of 3, but the next carbon over only has 1 hydrogen coming off it. It has carbons in that direction, carbons in that direction. So this would cause your peak for these hydrogens to split into a doublet. So a triplet means you've got 2 neighbouring hydrogen atoms, and most commonly for a triplet you'll see something like this. So this is a hydrogen environment that has 3 hydrogens in it, but has 2 neighbouring hydrogens. So the chances are you're probably looking at something like this. So this peak, the triplet, is worth 3. It represents these 3 hydrogens, and the reason it's split into a triplet is because it has 2 neighbouring hydrogen atoms on the next carbon across. And a quartet says that you have 3 neighbouring hydrogens. So the chances are that if you get a triplet worth 3 and a quartet worth 2, that this triplet is for these hydrogens, and the quartet is for these hydrogens, because that's showing that it's worth 2 hydrogens, but it's got 3 neighbouring partners, which are the 3 neighbouring hydrogens, which are the red ones. So a singlet, doublet, triplet, quartet tells you how many neighbouring hydrogens you've got, and to figure out how many neighbouring hydrogens you've got, you need to look at the number of peaks and then subtract 1. So 1 minus 1, no neighbouring hydrogens. 2 minus 1, 1 neighbouring hydrogen. 3 minus 1, 2 neighbouring hydrogens. 4 minus 1, 3 neighbouring hydrogens. So remember, whatever the splitting pattern is, subtract 1, and that will tell you the number of neighbouring hydrogens. So if you can figure out how many hydrogen environments you have by looking at the symmetry of the molecule and figuring out which of them are in equivalent positions, like this one, and this one, if you can use your data table, which I'll bring in now, so that's this table which you're given on your data sheet in your exams, if you can use that to look at the chemical shift value and figure out what sort of environment your hydrogens are in, if you can understand the splitting patterns in terms of singlet, doublet and triplet, possibly quartet, and if you can use the integral values to figure out how many hydrogens you've got in each environment, you can put all of that information together to be able to determine the structure of whatever it is that you've put into the NMR machine. So this one, the hydrogen 1 NMR, usually you can come up with a better idea of what the structure is than with carbon NMR, because for example with carbon you don't know how many carbons are in any particular environment because you haven't got any splitting patterns. You haven't got any integrals. You don't know how many are neighbouring because you haven't got any splitting patterns, and so on. So as long as you can use all of those things, most of them you've learnt with carbon NMR, then you can understand hydrogen 1 NMR. Now, just before this tutorial finishes, one last thing that you need to know for hydrogen 1 NMR. For the standard, obviously we include TMS, tetramethylsilane, to give us a value for 0 so that everything else is measured against it and we can figure out what our chemical shift values are. You also will need a solvent that you can put your organic compound in so that it dissolves, so that it can be read by the hydrogen 1 NMR machine. Most solvents that we would use would have hydrogen atoms in it, and because we're using hydrogen 1 NMR and we're detecting hydrogen nuclei, it's important that the solvent that you use doesn't have hydrogen atoms in it. So there's a set of compounds that we use called deuterated compounds, and these don't have any hydrogen in them. In place of their hydrogen atoms, they have deuterium atoms, which is H2, so hydrogen with a neutron. And H2 is not the type of nucleus that is susceptible to NMR. It won't flip and it won't relax back to its natural state. It won't give us peaks. So one example of a deuterated compound that we could use as a solvent is CdCl3. So that's carbon with a deuterium atom and 3 chlorine atoms. So had this been hydrogen instead of deuterium, this would be known as chloroform. And with the hydrogen atom replaced by deuterium, this is known as deuterated chloroform, and this is the solvent that we would use for hydrogen 1 NMR. And that's all for now. I will do a separate tutorial on how to put together all of these bits of information from the NMR spectrum to be able to determine structure, but for now it might be worth you having a go at that yourself.